Atsuhi will give this talk on maximally graded matrix factorizations and gamma integral structure for invertible polynomial chain type.
Thank you very much. Thank you very much again for the invitation to this conference. I'd like to talk on this. And what I want to do today is to explain the structure of the category of maximally-graded matrix factorization for invertible polynomials of chain type. And what I want to say is it is very similar to the category of coherent shapes on projectives. And also, I'd like to compare, discuss some homological mirror symmetry on the level of the homology group. So I'd like to start from recording this definitions and terminologies. Some slides are almost the same as yesterday, but just to remind the definition and notation and so on, I prepared this. And so this is our main object to consider invertible polynomial. It's a polynomial in n variables with n monomials. Here and this is point, and it is controlled by this combinatory data invertible matrix E. And so this is already explained yesterday, but in general, so invertible polynomial is a Thompson-Sebastian sum of these two classes. So, and this one, the chain type polynomial is of our interest today. And yes, also I consider group of symmetry as F. And Landau-Ginzburg-Oberhold is just a pair of the polynomial together with a subgroup of this maximal diagonalism. And so, in order to discuss mirror symmetry, we need to consider the Bergrun-Hughes transpose. It is an invertible polynomial defined by this transpose of the E. So in this way, by using the transposition of the invertible matrix E, we can define another invertible polynomial, which is denoted by F tilde. And today also, so to this F, I will discuss some algebraic aspect. And to this F tilde, we associate geometric object or geometric invariant. Now, this is the particular statement of mirror symmetry for Landau-Ginzburg-Oberhold. So so today I consider this pair on the algebraic side, F together with the maximal symmetry group, and in the geometric side, I consider to be trivial, the simplest case. And so usually we should do in order to consider mirror symmetry. First, associate combinatorially or algebraically to this pair algebraic object, and also to this F tilde geometric object. And we formulate a statement to identify them and prove the statement. Okay, so just in order to recall this situation, we just show this slide. So this is the category associated to this F tilde, derived category of directed Fukaya category of F tilde. It is very roughly speaking categorification of distinguished spaces of very vanishing cycles. But today I can only consider some homological level or just the middle homology group or the relative homology group associated with F. And so this is for the safety. I prepared again the notion of the full exhibition of collections. It's some certain algebraic or categorical version of the algebraic aspects of this in spaces functions. Okay, so so today this will be always mu tilde, which is equal to the Milnor number of the F tube. Okay, so now again, I'd like to recall the what is maximally graded matrix factorizations. So, in order to consider Z-graded triangulated category, we need to upgrade some GF to some abelian group of rank 1. This is the, exactly that. So this one. So this is a abelian group generated by these letters, Zi, A vector, and F vector. So these are considered to be some degree vector associated to each variables and polynomial F. And it's similar to and we consider such a relation. So that if the polynomial F is homogeneous with respect to this grading. And in the similarly to the usual Z-graded case, we consider the similar notation. So by this, I mean the grading shift by degree vector L. And this is a definition of the matrix factorizations. So it is almost the same, but just I prepared just to recall the notation. So these F0 and F1 are free modules, graded free modules, and F0 and F1 are morphisms satisfying these modules. And so again, so maybe I can skip this part, but anyway, in the usual way, we can consider the homomorphism and the non-homomorphic morphisms, and so we can consider naturally a homotopy category of the LF-graded matrix factorizations. And it is very nice category. So it is finite. The home space are all finite dimensional vector space, and any object can be decomposed into the indecomposable form. And also it is idempotent complete. A very nice category. And so this is a little bit different from yesterday. So today I use the particular matrix factorizations, and essentially this is considered by Daisuke. So suppose we have this graded module given by the quotient or by regular sequences, Then by considering the Cauchy resolution of this one, we get naturally, or we can naturally associate this Cauchy resolution of graded matrix factorization in this way. It's a little bit technical, but this kind of matrix factorization will be generated of this such category. So yesterday I already explained, but this is a very typical example of the simplest case. So we have, by considering this resolution, we get this matrix factorization. And so I denote this matrix factorization by C stabilization of this simple module. And roughly speaking, so some very rough structure of the previous, yes, this one, M stub, is the exterior product of this very simple. at least on the level of Grothendieck group, it is so, because we can just forget about these morphism, and we can have some how to say exterior product of this degree data. Okay, so again, this is the preparation for the notation. So by this, I mean the degree shift autoequivalence, and by t, the translation factor, and t square was the t square is equal to the f vector shift, as explained yesterday. Yes, so this is this statement, and so on this category, we have a cell factor. This is given by Auslander writing duality. Okay, so and this is new slide, and how to study this category. So because at least I believe in the mirror symmetry or homological symmetry, I believe in the existence of free expressional collection in that category. And in order to show that, we can do in the following way, or this is the key lemma to show the existence of the free expressional collection. And so in order to do that, first we need to choose or find enough number of good exceptional object or good matrix factorization. Anyway, we need to choose by hand. And so here, so because we should have the homological mirror symmetry equivalence, this should be the mirror number of f tilde, not f. So this is an important point. Anyway, first we need to choose somehow choose enough number of exceptional objects, and then by showing these two properties, then we can show that the exceptional collection is full. So this is a little bit a slight modification of the statement given by together with Kajiura cycle. Anyway, so therefore by using this, so once we have good matrix factorization, then and if we can show this, we are done. Okay, so now I will recall what is the homological mirror symmetry equivalence. We expect this here, the algebraic side, and this is the geometric side, and here we have f and LF graded one, and this is a category given by f tilde together with trivial. So so depends only on f tilde. And so today I skipped this part, but later in some example, in one example, I can show it. But anyway, so
I have a question.
Yes.
So the Fukai category is usually this G grade.
Yes.
So the
Z grade.
So the isomorphism and the G grade.
All Z graded triangle. So that's why I'm interested in the graded version of matrix factorization. So if we consider the ungraded matrix factorization, then this will be equivalence of Z over to the graded triangulated category. And it's a little bit difficult. So I prefer this.
Is it supposed that this quotient CQ modulo 5 is finite dimensional?
Yes. So it automatically follows from this.
Finite codimension.
If it yes, so this is equivalent to the existence of full strongly exceptional fraction. Okay, so from now, so I only consider the invertible polynomial chain type. So we consider this one. And for later purpose, I denote this polynomial by Fn and this polynomial ring in n variables by Sn. And also, for simplicity, we assume that these exponents Ai's are all greater than or equal to 2. Then LF is given by these relations. And so it's a little bit complicated, but anyway, so from this relation, it's easy to see that this group, this abelian group, is generated by this element Z1. And in particular, if we consider quotient by this element, this is n, then we get these relations. So therefore, I mean, this group is of order Dn. So it's not so complicated, but it's rather easy object. Okay, now I'd like to state the first statement. So by this, I want to say that there exists a very nice full exceptional function. It is, in some sense, given by this object together. Essentially, this one, and it is controlled by this object and all the variant stuff. And I'm sorry, I don't think so. I don't say what this tau is, but anyway, here I just want to say the existence of some object and some autoequivalence, and such that this will be a full exceptional collection of this category. And also, so the Milnor number of the dual polynomial is rather simple, and this is already appeared in the singularity theory in early 80s. And this is very combinatorial. And the important point is that it's a little bit, so here I didn't say what E is and what tau is, but anyway, it's easy to write down the Euler matrix in this way by using the principal nilpotent matrix. This is a statement. Later, I'll explain a bit more about E and tau, probably in the next slide. Anyway, so I also explain in one example. And but before, I'd like to say something about this statement. And so the existence of full exceptional collection in this category is first proven by Hirano and Ochi. And so I heard their story. I considered again this problem and then soon found good full exceptional collection. Anyway, and this one of the important motivation is this one. So there is a how to say some motivation in the singularity theory, and so it is the Ulrich-Randall conjecture. So which says which explains the existence of distinct basis vanishing cycles whose Seifert matrix is of this form. And also, what is important is the similarity to the general category of product space. And so previous E is the analog with structure shape in this category. And tau is the analog of the tensor by O1. And in this case, in the PN case, project space case, this Euler matrix is given by in this way in terms of the principal nilpotent matrix. And also this is the how to say the from this expression probably you can see this. So if you write in this way, you define a polynomial n plus 1 maybe. And this is nothing but the Poincare series of the coordinate ring of project. And it is obvious by the choosing of the by the choice of the auto equivalence. But anyway, so just in order to have an Euler matrix, we need to only put here a principal nilpotent matrix. That's the important point. And we do this similar thing if for theory of the this graded matrix factorization. Anyway, so more precisely, so in the categorical language, we can say this similarity in the following way. So both these categories have the so-called left-shift decomposition in the sense of Kuznets model. So it consists of the object and autoequivalence generating the category. And in this case, so our E is the analog of the structure shift, and tau will be the analog of this, and the analog of Poincare series will be this one. And also in this context, this kind of the object was considered as the characteristic polynomial of the Milnor monodrome. And so, together with such an observation, they conjecture the existence of such this nice distinction. And in some sense, our result is the proof of the algebraic statement of their conjecture. Now, I'd like to explain a bit how to choose exception object E. It is given by the very particular matrix factorization of this form. So once we know the answer, it's very easy. But if we don't believe in the existence of such left-shift decomposition, it's quite difficult to find or to see that this matrix factorization is a good one. That's a difficult point. And once we know some possible answer, then it's rather easy to find or rather easy to see that this is the good one. And also that tau, it is nothing but this translation, grading shift operator. And so by calculating the characteristic polynomial in the Grothendieck group level, it's easy to see that this is the Poincare series or zeta function of this induced automorphism of the tau. And so here I wrote something about the relationship between these autoequivalence and this Poincare series or zeta function. Anyway, so the important point is that in this just maximally graded matrix factorization category, it's very easy to, how to say, study this cell functor. That's the point. Okay, now I'd like to explain my some examples. In the first case, it's very easy. Of course, already. So sorry. In the first case, so if so here a equal 1, then it's very easy.
Does the monodromy use some natural autoequivalence of the matrix factorization?
Monodromy, you mean Milnor monodromy in the geometric side? Yeah, it is nothing but the cell functor shifted by 1, translated by 1. Sorry. S this is the maybe this is the Milnor monodromy.
That's in the geometric.
Yes, in the geometric side.
And in this setup, it's expected to be the same.
Which one? How?
Matrix factorizations. Does one have a priori function of the monodromy on the category of matrix factorizations?
Yes, so it's so essentially in the next in this case, the simplest case. Sorry, again, it's a bit difficult. Just a moment. So, it is. I'm sorry. My head is almost sleeping. It's difficult to calculate, but in some ways, so they are related. Sorry, how to say? Just one switch. In this, if n is 1, as far as I remember, if n is 1, then tau is the inverse of, I forgot here, just one moment. I forgot, but anyway, something like this. It's just not, no.
So what is your tau? Auslander right?
Auslander, yeah. Auslander right hand translation or inverse of Auslander right hand translation. I forgot which is correct.
Well, Auslander right translation is Servante composed with schema.
Yes. And so the problem is here. I forgot which is and so in this case, up the sign or the direction of the rotation, the tau coincide with the Milnor model or Auslander right hand translation. And in this case, this Euler matrix is the usual upper triangular part of the Cartan matrix of type A. And the next case, this is a little bit non-trivial. In this case, we have this one, and here we have a quiver with bridge. It is called the Nakayama algebra. So it is given by the A quiver of type A with this relation. So in this case, this is the generator. The first part of the generator. And by using the copy, in some sense, a copy of this object, we can generate the whole category. And in this case, so it's very easy to calculate the home space of this matrix factorization. It is given in this way. So we get easily the dimension of the home space, which is this Euler matrix. So essentially, this is because so here this one is generated by the home space is generated by Z, whose relations is given by this one. So here in the numerator, so in the denominator, so corresponding to Z, we have 1 minus n, And here we have a relation. It is z to a1. So here we have in the numerator relation.
So let me try to rephrase
Yeah.
the previous question. We have S composed with T minus 1, well defined on the category of matrix factorization.
Yes.
If you take the Hawkian cohomology, does that induce the monodromy on the cohomology of the unifier?
In this case, because here now we are considering the LF graded version, the Hochschild homology group or Hochschild cohomology group are different from the Jacobian being or such a Jacobian molecule omega L. So it is anyway we are considering a different category. Anyway, so on the suitable invariant, so the induced automorphism acts naturally. Anyway, so these are typical examples. And here, in this case, because we are very lucky, so here we have just a usual algebra. But in general, so for example, if n is greater than or equal to 3, then in general we get as an end. So anyway, not the usual algebra, but we will have a DG algebra. And also the quiver with relations are quite complicated. So therefore I cannot write down in a unified way. So this was about some structure of the category. And next, I'd like to discuss about the integral structure. This is about the I'm going to discuss about some compatibility with the mirror symmetry isomorphism. And first, I'd like to explain a bit on the P and K. Because the structure is very similar. So first, I'd like to explain in the usual states. And so this one, this gamma integral structure was introduced by Itani and Hasar contribution until, and it is defined by this kind of map. And here, the point is here we have some characteristic function defined by the gamma function. These are the Chern roots of the some maybe vector bundle or something. And here, this one is the modified Chern character. So it's defined by maybe this one is sum of not e to delta I, but e to 2 pi I delta I. Here we put 2 pi I. So this is corresponding to the modified. So here it's modified. This is necessary because of the natural weight in the sense of Hodge structure.
What is the
Sorry.
capital gamma?
Capital gamma. Capital gamma. This is gamma function.
The usual gamma.
Yes. So in gamma function, formally we put this one, and in the usual way, so we can expand to get some certain characteristics. Right? And so by using this Chern character twisted by this gamma character, we get some natural integral structure which in studying mirror symmetry. So in the usual, so of course there is usual integral structure also, but it's not. It doesn't behave well under the mirror symmetry isomorphism. So we need to twist in some sense so that we have a compatibility with the mirror isomorphism. So this is the role of this gamma function or gamma cap. And so this is the definition of the integral structure of this vector space homology group. And this 1 over 2 pi I to n, this is necessary to for the anyway due to the weight reasons. And so now I want to consider mirror dual object to this Pn. This is a natural generalization of the of Jorgen explained yesterday. And so this is the rational function. And together with this particular choice of the volume form, it will define a mirror dual object to the project. I mean, if we replace the holomorphic volume form, then we get another mirror or some different model. And so here is the natural generalization of the factor I explained yesterday. And so this is module over free module of rank 1 over the Jacobian algebra associated to this F tilde Q. And this one is very natural Fourier abelian group for this model. Or relative homology is the anyway the natural one. And in the singularly setting, so because of the this here, usually here we consider C to N. So because it has non-trivial homology group, so it will be isomorphic to the middle homology group of middle fiber. But in general, it's better to use this one. But anyway, so this is the what we want to consider as a integral structure in the mirror dual side. And this is naturally this can be naturally embedded into this cohomology group by this Poincare duality map. And this is I omitted some explanation, but anyway, this is isomorphic to this vector space. So by combining these two maps, we get integral structure inside of this by using the natural Poincare duality. This is the integral structure in the mirror dual. Okay, now this is a statement by Galkin, Gorisho, Militani, and Militani. So this is the, in some sense, the homological mirror symmetry isomorphism on the level of Grothendieck group. By using the point is by using this gamma integral structure, this map comes. And here, this one is mirror isomorphism or topological mirror symmetry isomorphism. So in this sense, this gamma integral structure is very important. It is the natural mirror dual integral structure to this the very natural one in the geometric side. And so here, for simplicity, I explained it by taking a project space, but this can be naturally generalized toric overform, weak fan toric overforms by these people, both Korki, Itanitsen, and Ita. Okay, now I'd like to come back to our setting, matrix factorization category. So here, so in order to discuss such a commutative diagram, we need topological mirror symmetry isomorphism. So I again prepared these notations and so on. So this is the same slide as yesterday, and so this is the what we want to consider as a vector space. This will be the analog of the cohomology group of the projective space. Sorry, I wrote here nonsense. Anyway, so yesterday I explained already, but so in this particular case, for chain type polynomial, I'd like to explain a bit more about this topological mirror symmetry isomorphism. So in this chain case, this space has this kind of inductive structure. So yesterday I explained this part when the number of variables is 1. And in general, so maybe here, this xk part, this forms a monomial basis of the Jacobian ring, and it is given by this combinatorial property. This forms a anyway, so x to k with this condition form basis of the Jacobian. And I'm sorry, yes. No. So plus something coming from f tilde n minus 2. That's it. And so also just I got confused. Yes. So this is the how to say the in the geometric side with fn f tilde. And so yesterday, I by using the inverse matrix, I explained a bit on the weights of variables. So this is the generalization of that one. So this is what I wrote by Q yesterday, Qi. But today, of course, today I did not do it by omega. So this k1 to plus 1 to kn plus 1 is in some sense the exponent of this how to say multi-exponent or something of this one form not one form but differential form. And these how to say as I write here these omegas are considered as a weight of this differential form with respect to the isocoordinate. And by using this a little bit technical object, we can write many things. But anyway, so I think. And also, so I already mentioned that GF, the finite group, is a cyclic group of order Dn. So this is LF, essentially same as the, very roughly speaking, just Gn. This is essentially same as this. So it is generated by one element, cyclic group, and it is of order Dn, the product of A1 to An. And by preparing some element, we can write down the basis of the dual space. So this one. Maybe I direct skip some technical part. But anyway, so here again, inductive structure. So here is a part corresponding to the previous one, this one. And here there is some part coming from n minus 2, and here from m minus 2 again. So each corresponds to each part. So based on this inductive structure, we can show the topological mirror symmetry as well. But in order to do that, we need to identify the two kinds of indices. So I mean the kappa and I. So here's the discussion about this. So here k was the exponents of the this part of differential form, and kappa corresponds to this group element. And the point is, in order to for the proof of the topological mirror symmetry isomorphism, is this existence of the bijection between two indexes. This is the key point. And also some one-to-one correspondence between two rational set of rational numbers.
Sorry, the AI, I forgot the AI.
AI was the exponent of the defining equation.
Yeah, the question is if they are very well coprime or not.
We don't assume any condition, but except for this. Any numbers are okay.
Any numbers are okay. So then the group GF, why is it cyclic of order, the product of?
Yeah, essentially these relations together divided. Or by this explicit presentation. Yes, this one. So here, one more thing. Essentially, this is a relation. Anyway, so but this is important about the technical part. I just wanted to show, and but I can skip. Now I can I'd like to explain a bit on the how to define the gamma integral structure. So first, I need to prepare some mu tilde by mu tilde matrix of this form. And so just I want to show this. So about some rough structure. So in order to how to say identify or make isomorphism between two different kinds of index sets, we need some connection matrix. So here, this matrix has indexes J and kappa, and two different kinds of indexes. But anyway, both by how to say. Anyway, this by this kind map side, two sets are identified. But anyway, so in order to connect, we need this kind of some at least some matrix, and it will be some important matrix or important map weighted to the modified Chern character twisted by gamma character. And here is the last sketch. So you can just forget about this. I'll explain later a bit. But here, so first here I want to say here again inductive structure. So this 2 by I comes from the Tate twist. And so here this question C kappa consists of 2 parts. This is important part. Something with gamma function and also this one. And I want just show this. But anyway, so I want to explain in this way. So first part, the gamma function part, this can be considered as the gamma class on the kappa sector of this omega G. So this is the analog of the gamma character on the kappa sector. And the next part, this one, just this one, the later half. This, sorry, this combination of this, this is should be considered as the Chan character of the matrix factorization. This is given by Polshuk-Weintraub. And so, very roughly speaking, this one, yeah, it's very difficult to see. But anyway, this is roughly some degree data of the matrix factorization of this particular one. So we considered these particular matrix factorizations, and corresponding to these two cases, we have this one. So essentially, this comes from the degree data of the matrix factorization. So therefore, as I explained yesterday, so degree data is somehow related to the homology class or class in glutamate group. So it is nothing but the Chan character part. And by combining these, we have some Chan gamma. And the last part, this is related to this equivalence part. So therefore, totally, very roughly speaking, this combination will define some good matrix. This is the explanation. So totally, so what I want to say is this. Just this statement is enough. This matrix is the matrix representation of this some Chan character twisted by gamma character. Okay, so by using that matrix, so here on this base we have a good basis. So by using the matrix representation, we can define a map. And so we consider by using this, we consider the gamma integral structure. So I forgot to say, because this has a free expression approximation, this Grothendieck group is free available. So the image of this defines inside of this vector space integral structure, which I call the gamma structure, the integral structure of this graded matrix factorization. And on the other hand, so this is the classical and standard one. In the geometric side, we have the natural integral structure inside of this omega f tilde. So now we can compare. So this is the result. This statement is exactly analog with an known facts for projective space. So the existence of isomorphism between this relative homology group with the Grothendieck group. And by using the previous topological mirror symmetrical isomorphism, we have this commutative line. This is a statement. And this shows the compatibility with the homological mirror symmetry and topological mirror symmetry and so on.
You also have a statement where the role of the groups are switched. There's G, F, tilde, and on one side, and the trivial group on the other side.
Here, yeah, it is inside of what I skipped somewhere. So here, this one, the correspondence between these and these. Here I use that. So here we have a differential form. It is mirror dual to this group L, or the constant function on the some fictor locus by this L. This is the some mirror correspondence. Where I use the mirror symmetry of this one and this one. And also the existence of flexible collection is used to show that this is a free abelian group of the expected one. And I didn't explain, but here, in order to get this one, I construct directly a cycle here by hand. So, but it's possible because, so maybe in the next slide I prepare. This is a key fact. So here we consider the this integral, but because this is the polynomial chain type, so it's very easy to calculate that calculate in this way, but in terms of the gamma function. It's a kind of the exercise for undergraduate student. And also to determine a cycle is to determine the value of this integral for all possible k. It's just some pairing of the homology group and the cohomology group. And so this is, so once this is fixed and by considering all integrals, then we can determine this. At least in the homology group with real coefficients. And also somewhere, so I use something. But anyway, based on this, essentially based on this, we can determine which one is the anyway. So by hand we can construct the good cycle. At least one cycle in the relative homology, which defines a class in relative homology, and the others can be constructed by this automorphism. So in the algebraic side, sorry, in this side we have the autoequivalence, and it defines in the geometric side some geometric automorphism, and this corresponds to the geometric automorphism in the mirror geometric side. It is given by this.
So that's an automorphism on what? What is it?
So this acts
X1 to
X,
Xn?
X1 to Xn are coordinates on the geometric side. Zi to Zn coordinates in the algebraic side. I distinguish these two. Okay, so it's a little bit complicated, but so this is so here f tilde, not f, and here I used x. On this x spaces, so tau, essentially this group, anyway, some automorphism acts in this way, and by this action we have enough number of cycles in the geometric side. So in this way we can compare, or at least in this way we can have this isomorphism of free abelian groups. And also, so we can identify several important invariants. This time I didn't discuss about the Frobenius manifold structure, but so there we can consider Stokes matrix and central collection matrices as a mononomial data. But they are identified with the geometric invariants such as Seifert matrix and monatomic data. And so here in this story, the important point is that Euler matrix can be identified with Stokes matrix and Seifert matrix. It is very important. By this, anyway, so we have this commutative data. But here, we haven't proved the homological mirror symmetry equivalence, but nevertheless we can construct some isomorphism of the variables between these two. And so this is the last one. So based on this previous picture, it's natural to expect this one. So this one again, I haven't discussed about bridge-round stability condition, but on this category of graded matrix factorizations, I expect there is a natural construction of the so-called Gepner type of stability condition. And it should be given by this, by using the oscillatory integral. It should be defined, I expect. At least for the simplest case and AD case, it is true. And so based on this, here for example, so in this, by using this, so we can construct a very natural and special stability condition. And by using that, we can characterize one particular Dinkin diagram. And so in this way, at least in the AD case, we can have as a special Hochstetter Dinkin diagram the usual one. So this is related to some problem I